What were the very first lights in the universe? Not the Big Bang glow, but the first stars, the cosmic pioneers that ended the Dark Ages. Finding them is one of astronomy's biggest challenges. Even the mighty James Webb Space Telescope might not be enough. Just a few years ago, Hubble held the record for the most distant galaxy. GNZ11 was seen as it was only 420 million years after the Big Bang. It was an incredible achievement at the time. Then came JWST in 2022. With its larger mirror and infrared capabilities, it quickly shattered that record. JWST can see objects invisible to Hubble. As of May 2025, the record holder is MOEM-Z14. Its light comes from just 280 million years after the Big Bang. That's 140 million years earlier than Hubble's record. JWST has found hundreds of ultra-distant galaxy candidates. It's pushing the boundaries of what we thought was possible. The early universe is being revealed like never before. Despite its power, James Webb Space Telescope can't see everything. The farther back we look, the denser the universe was. It was also filled with neutral hydrogen atoms. These neutral atoms absorb short-wavelength light, like ultraviolet and visible light. This is the light emitted by hot, young stars. Even though JWST sees this light redshifted to infrared, it still originated at shorter wavelengths. If too much neutral matter is present, the light gets absorbed completely. It never reaches our telescopes. This extinction is a fundamental barrier. So far, JWST hasn't confirmed any galaxies beyond about 250 million years after the Big Bang. The galaxies it does find show signs of being well evolved. They contain heavy elements from previous generations of stars. We aren't seeing the very first stars with JWST. They must be hidden by this early cosmic fog. We need a different way to look. The first stars, called population 3 stars, would be made only of hydrogen and helium. They would be massive and short-lived. When they died, they would create the first heavy elements like carbon and oxygen. Finding these pristine stars or their immediate aftermath is crucial. It tells us when and how the cosmic dark ages ended, but the light they emit directly is likely blocked by the surrounding neutral gas. A brute force approach with JWST might find slightly earlier galaxies, but it's unlikely to find the true first generation. The extinction problem remains. We need to find a signal that isn't absorbed by neutral hydrogen, a signal that can travel freely across the universe. This requires looking at longer wavelengths. One possibility is to look for light emitted at longer wavelengths from the start. While starlight is absorbed, other signals might not be. These signals could come from the elements created by the first stars. When the first stars die, they produce carbon and oxygen. These elements emit light at specific far-infrared wavelengths. For example, singly ionized carbon emits at 158 microns. Neutral oxygen emits at 63 microns. Doubly ionized oxygen emits at 88 microns. These wavelengths are less affected by neutral hydrogen absorption. At extreme distances, these far-infrared lines are redshifted. They arrive at Earth as millimeter or even centimeter waves. A telescope sensitive to these wavelengths could detect them. Future observatories, like the proposed Origin Space Telescope, could target these signals. They could reveal star-forming regions in the early universe. This could be our window to the first star's impact. Finding these specific emission lines would provide evidence of the first heavy elements. This, in turn, points to the death of the first stars. It's an indirect but powerful way to probe that era. This approach relies on detecting light produced after the first stars have lived and died. It traces the consequences of the first star formation. It bypasses the extinction of the initial starlight. Perhaps an even more powerful probe is the 21-centimeter line. This signal comes directly from neutral hydrogen atoms. It's a signature of the gas that filled the early universe. A neutral hydrogen atom has a proton and an electron. Both have a property called spin. In the lowest energy state, their spins can be aligned or anti-aligned. The anti-aligned state is slightly lower energy. An atom with aligned spins will eventually flip. When it does, it emits a photon with a wavelength of 21.106 centimeters. This spin-flip transition takes about 9 million years on average, but with vast clouds of neutral hydrogen, this creates a constant, faint glow at 21 centimeter. This signal is not absorbed by other neutral hydrogen. The 21 centimeters line allows us to trace where neutral hydrogen exists. We can see the gas before it forms stars. We can also see where it's being affected by the first stars. When the universe first became neutral, 380,000 years after the Big Bang, it was full of hydrogen. As the first stars formed, they ionized the gas around them. This created bubbles of ionized gas within the neutral medium. The 20 Fresnel Players signal can map these bubbles. It can show us the process of reionization, driven by the first stars and galaxies. This gives us a direct view of the early universe's structure. The wavelength of the 21 centimeter signal is redshifted by cosmic expansion. For the era of the first stars, redshifts 1550, it appears at wavelengths of several meters. This is in the radio part of the spectrum. Detecting these faint, redshifted 21 centimeter signals is difficult. The biggest challenge is interference. Earth is a very noisy radio source. Human activity, from cell phones to TV broadcasts, creates radio waves. These signals are far stronger than the faint, cosmic 20 centimeter glow. They drown out the signal we want to see. Even radio telescopes in space near Earth are affected. We need to get away from Earth's radio pollution. There's one ideal location in the solar system. The perfect place to detect the faint 21 centimeter signal is the far side of the Moon. This side always faces away from Earth. It is shielded from our planet's radio noise. Building a radio telescope on the lunar far side would provide an unparalleled view. It could be a single large dish in a crater or an array of smaller dishes. This location offers a quiet environment for sensitive radio observations. Such an observatory could map the distribution of neutral hydrogen across cosmic time. It could show us when and where the first stars began to ionize the universe. This would be a revolutionary step in understanding cosmic history. Mapping the 21 centimeter signal could take us back even further than JWST's limits. It probes the gas that formed the first stars. It's a direct window into the cosmic dark ages and the dawn of the first light. JWST has taken us closer to the Big Bang than ever before. It has revealed galaxies from just a few 100 million years after the start. Its discoveries are transforming our understanding of cosmic evolution. But finding the absolute first stars, the pristine population 3 stars, remains a challenge. JWST is fundamentally limited by the absorption of light by neutral gas in the early universe. We need new tools and new strategies. The search for the first stars requires looking beyond the light they initially emitted. We need to find signals that can escape the early cosmic fog. Far-infrared emission lines from the first heavy elements are one possibility. What do you think is the most exciting way to find the first stars? Let us know in the comments below. If you found this journey through cosmic history fascinating, please give this video a like. Subscribe to our channel for more deep dives into the universe's biggest mysteries. And don't forget to share this video with fellow space enthusiasts.